Sometimes you just want to knock a system off the network. Sometimes you want to just cause trouble. So we can do a denial of service with that. Denial of service, and we've mentioned this before, is a network-based attack. It prevents the target from performing normal duties. Distributed denial of service is where we have many attackers coordinating to attack one target. And we're talking thousands, hundreds of thousands, to basically either knock that target off the network or just keep it so busy it just can't function. There are many ways of doing denial of service. We could just flat out flood the server with network traffic. We could crash the service. We could eat up all its available resources, all the CPU, all the RAM, the disk space, the available connections. And denial of service can be aimed at a particular protocol, aimed at a particular operating system, or aimed at a particular service running on the operating system. So here are some denial of service attack types. There's ping of death. Now, what ping of death is you ping something, but you take a ping packet and you chunk it up into fragments. And when the pieces reassemble, the ping is too big. It's out of bounds because in networking, you have a minimum and a maximum acceptable size. The fragments by themselves fall within those bounds, but when you put it together, the actual ICMP echo request is too big, and some devices will crash when they have assembled something that's too big. So that's the ping of death. We send an ICMP echo request larger than 64 kilobytes, but so that it actually makes it, we send it as fragments. That's typically how it's done. Or we can just send not just ping, but any other kind of packet, ICMP, UDP, TCP, as fragments. And they're either just too big, or they can't be reassembled properly. We deliberately make it so that the reassembly doesn't work, which will crash the target, or panic the target at least. And with that TCP fragmentation attack, we have sequence numbers that are overlapping, or the IP fragment offset is overlapping. The earlier versions of Windows and Linux were the most vulnerable to that. Or you can have something called a Smurf attack. Now, the Smurf attack is fun because I have a number of things. Let me just get some examples here. So here's a target, here's me, and I've got any number of normal hosts in the middle between us. And so here's me over here. I am going to send a fake ping, a whole bunch of them, fast, not using the operating system, but real quick. A fake ping to all these normal machines, just normal machines doing their thing. And the source is not me, it's the spoofed address of my target. So I'm sending all these loads of fake ICMP echo requests to all these things in the middle. They don't respond to me, they all respond to my target and knock him off. That's called a Smurf attack. So we're sending large numbers of spoofed ICMP echo requests to intermediate devices that all respond to the target. We could flat out flood the network with lots of packets. We could flood the network with lots of packets that are trying to establish a TCP session, a SYN flood. It's kind of like ding dong ditch, right? So you ring the doorbell, you hide. And the device is trying to SYN-ACK back to you and complete the handshake, and you're not there. In fact, you're sending it, it's not you, you're pretending it's coming from all these other sources. And it's trying to make connections back to those other sources, and of course they don't exist. Or their IPs are wrong. That's a SYN flood. And we could do it, usually we do it with TCP, but there are also UDP versions. We could have SMB, these are of course the file and print requests. We got the packet malformed. So when this thing receives an SMB request, it crashes the system, or at the very least does a denial of service. There used to be some famous denial of service, very few packets, malformed SMB requests that would cause a Windows machine to blue screen. And one of those famous ones was something called SMB die. And you basically had a target IP and a name, and then it would malform the request, what we call a named pipe request, and would cause the thing to instantly blue screen. It was awesome. And there are some other tools, other attacks. There's something called slow LoRa's. You keep fake web connections open for as long as possible until we've eaten up all the normal connections. So, and it in fact allows one web server to take down another web server without impacting anything else. Because we're not sending floods of just junk traffic. We're just keeping web connections alive forever so that it's too busy with phony web connections to take new ones from legitimate clients. We could do TCP Fragmentation Attack, like I said, TCP fragments that cannot be reassembled properly. We can do an NTP amplification attack. NTP is Network Time Protocol. So we send spoofed NTP queries to NTP servers to try to overwhelm a target with UDP traffic. What it is, it's kind of like a Smurf attack. You know, out on the internet, there are these authoritative time servers. The U.S. Naval Observatory is one of them. There's a bunch of others. And what you do is you send all of these phony queries to a time server because you've got corporate servers trying to synchronize their clocks with these authoritative sources. So you send all of these phony requests to an authoritative clock who responds back to your target and is overwhelming your target. So it's a variation of the Smurf attack, but using NTP. We could do an HTTP flood attack. We could just send loads of HTTP GET requests to a web server and overwhelm it to consume all of its connections. And in fact, with that, we don't even have to do spoofing or malformed packets. We just keep on saying, give me this and give me this and give me this, and it'll try to respond, can't keep up. We could do a DNS flood attack. So again, it is, we can either spoof like the NTP Smurf style attack, or we can just keep the DNS server busy with bogus queries and eating up all of its memory or CPU. Or we can do DNS amplification attack, which is Smurf, but with DNS. So I am using multiple public DNS servers that are receiving all these phony requests, and they're all responding back to one poor little machine. So loads of opportunities for doing denial of service. The term stress testing is just another polite way of saying denial of service. It's the process of determining the ability of a computer or a network or an application or a device to maintain a level of effectiveness under unfavorable conditions. You're basically doing denial of service. We can use a bot army, which is how we would do it distributed. We could run scripts or other tools. And often we stress test legitimately to see how much traffic could this website handle. In pen testing, you got to realize that when you do not denial of service to stress test, you are stressing the system. You're stressing the network and or you're stressing a target server. It can be destructive. So just be aware of that. So pen testers, you need specific authorization. Clients need to be aware that that service will probably be unavailable until we lay off, until we stop. So let's have a little fun doing denial of service.